Okay, my dear student, it's the last lesson of topic 3, which is energy levels in atoms and line spectra. In this lesson, we will study the following objectives. Let me read them together. Show an understanding of the existence of discrete electron energy levels in isolated atom, like hydrogen atom, and deduce how this leads to spectral lines. Number 2, distinguish between the emission and absorption spectra. Number 3, recall and solve problem using the relation delta E equal HF equal E2 minus E1 equal HC over lambda. Let me start together with this new lesson. To understand the aim of this lesson first, here in this lesson, we need to study the behavior of electron in the orbits or around the nucleus. What happens to this electron, how it moves from one level to another, or from one orbit. And to study this and understand the phenomena, we need initially to have an idea about emission and absorption spectrum. All of us know when we direct light right toward the prism, white light, we see a like rainbow, right? So this rainbow, we consider it as a spectrum. You see? Now we have different, in front of us, we have different forms of spectrum, as you see. Initially, as you see, we have, this is the normal lamp, we know, like tungsten lamp. When it's turned on, the white light, when it passes through the diffraction grating, we see a thing known as continuous spectrum. Okay? So this is the meaning of continuous spectrum. We see all colors. You see all visible colors. Okay. So okay. The second part of this picture in front of us, we see here hot glass. This hot glass, it's the gas inside the discharge tube. This like flow compact lamps we use, when we apply voltage to it, it produces white light. Okay, this produces white light, comes from the gas inside the tube, right, the discharge tube. When it passes through the diffraction grating, we see, as you see, like dark background. You see black light, but I see some colored lines. You see, so I see, we will call them later emission spectral lines. So these colors you observe here, we have like 7, 8 colors. Is it clear? Or 7 to 6 colors. These colors, okay, comes out these particles, the gas atoms inside the tube. So when we apply a voltage on them, they produce light. This light is analyzed here. So what we observe, what's shown here is called what? The emission spectrum, which include emission spectral lines. If you do a thing like opposite to this, we give all white light toward this gas, the previous gas, which was under low pressure. Then we let this light pass through diffraction grating. We see what I observed before, all the spectrum, but some of the color disappeared. The color appeared here, the lines appeared here, disappeared here. This is because I'm using the same gas. You see? So these lines, the dark lines, disappeared in the last spectrum. We call them absorption spectral lines. Absorption spectral lines. So the conclusion I can draw from this, that each atoms, okay, if I change the gas here, I see another emission spectral line. Even if I use the same gas here, I get another absorption spectral lines. You see? So the conclusion we can draw here, like any atoms or the spectrum represent the identity of the atom, because from one atom to another, the spectrum changes. So each atom has its own spectrum. and the spectrum changes from one atom to another. To understand this idea more, we need to study the energy states. We will understand that later. Okay, electron energy levels in atom. We need to imagine, here we will study the energy levels, the electron energy level in atom. We need to imagine, like, let me draw, if I draw you may understand better. We imagine this is the nucleus of an atom, like hydrogen atom. So this is the nucleus. So, and the electrons, they are around the nucleus, and we have many states of many levels of electron. So that you may find electron here, you may find it here, you may find it here, you may find it here, but you can't find it between these levels. Is that clear? So these are called what? The electron energy levels or energy states. So the diagram here, what we see here, this is for hydrogen atom. This energy states of hydrogen atom. Okay. The ground state we observe here is the closest to the nucleus. It's what is the nearest level to the nucleus. You see? So this is n equal to 1. So when we go away, okay, the energy, the way the nucleus, we see that the energy of the level increases. So we start with minus 13.6 and we end here with 0 electron. You see? Okay, to understand this more, okay, let's first we read together, then we go to the next step. What's written here, electrons in an atom can have only certain specific energies. And these energies are called electron energy levels of the atom. This may be represented by a series of lines against a vertical scale of energy. You see these lines? They represent the energy states or the energy level of electrons in an atom. To understand more or to know the energy of each state, here what's required from us is to work with hydrogen. To know the energy E1 for the first state, E2 for the second state, E3 for the third state, and so on, we can use this formula, En equal minus 13.6 electron volt over n squared. This formula only for hydrogen atom. For whom again? For hydrogen atom. We can't use it for other atoms. Is it clear? This is Bohr's equation. So, for example, if I need to calculate E1, the energy of the first state, simply I substitute 1, which is E, so minus 13.6 electron volt over 1 square. So the answer will be minus 13.6 electron volt. If I need to calculate the energy of the second state or the second level, so minus 13.6 electron volt over 2 square. For the third one, minus 13.6 electron volt over 3 square. E4, okay, minus 13.6 electron volt over 4 square, and so on. So we can't find the values here. Okay. Now let we move back a little bit, or before moving back. So N1, the nearest level to the nucleus, we call it ground state. What we call it? Ground state, or ground energy level, or ground state, same idea. Where the other states, what we call them? We call them excited states. Excited states, or excited level, same idea. And the last state here, we call it ionization state. Ionization state. Okay? So when we say E equal 1, it's okay, it's not excited state, it's a ground state. When E equal to 2, it's the first excited state. Excited state. You see? E equal 3, it's not the third excited, it's the second excited state, and so on. You understand? Okay, we move back to see the exact demonstration of this. So we see together here. After calculating E1, it's minus 13.6. E2, as we said, it's minus 3.39 electron volt. You see minus 1.51. So here we have a ground state, here we have first excited state, here we have second state. At the end, we have the ionization state at infinity. You see? Okay. Now we go deeply in the behavior of electron, what happens. What's written here that the electron and the atom can have the energy of any of these energy values, but can't have energy between them. Means, as I said before, if we have these energy states, right? We can find electron here. We can find electron here. We can find electron here. You can find electron here. You can find electron here. But it's impossible to get an electron between them here or here or here, because the electron can have the energy of one of these choices, either E1, E2, E3, E4, and so on, E5, but it can't have energy between them. This is very important idea. This is number one. Number two, the movement of electron between energy levels is called a transition. Later, we will see now, we will see later that the electron, for example, this electron, can move from this level to this level, from this level maybe to this level. You see? This transition or this jump, we call it a transition. What we call it, electron transition. So the electron may jump down, may transfer downward, and at the same time it can jump upward. You see, from lower to higher energy, maybe from here to this state. You see, so I have two types of electron transition: either downward transition or what, or upward transition. But when the electron undergoes a transition, when electron undergoes transition, it's either gains energy or lose energy, or loses energy, right? Because if it's going to higher energy state, it needs to gain energy to move up. But if it will jump to the lower energy state, it should lose energy because it's changing its energy. This is the concept. Okay, let me see the difference. Here in front of us, we have a diagram showing demonstrating two different jumps. See, here the electron is down, you see? So to move the electron up, it needs to absorb energy. From where this energy comes from? It absorbs a specific photon to move to this state. So when the electron absorbs a specific photon, it jumps to a higher energy state. Okay, let me explain that more. So the first idea we need to understand. Imagine I have here two energy states. This is E initial is equal minus 4 electron volt, and E final equal minus 10 electron volt. This is not hydrogen, maybe another atom. And I have electron here. When this electron jumps from E initial, to E final, it will lose energy because initially it had minus 4 and now it becomes what? Minus 10. So here we have loss of energy. You see? The student will ask me how it loses energy. It loses energy in the form of photon. It radiates or it emits photon. You see? So it loses energy in the form of light, as photon, where the energy of this photon, it's equal to the change in energy, which is always the greater energy, the higher, and here the higher is whom? Is the initial. So I initial minus I final. You see? So which will be in this case equal to -4. Always I substitute the greater first, then the smaller. Why? Because the energy scalar quantity should be positive. So the answer will be positive 6 electron volt. See how we work? This is the first type of transition. We call it, what we call it, downward transition. Downward transition. Okay? So every time we have downward transition, the electron loses energy as photon. And this is the way how we calculate the energy of the photon. And this is corresponding to emission spectral line we studied before. Emission spectral line. So here we have emission spectral line. Because this jump produces light, photon has a certain color represented by emission spectral line. Now the second case is the case of, so here this case number 1 was the explanation of this part. Now I need to explain the second part, the case of absorption. Concentrate with me. So now we need to consider, we have another consideration. Let we imagine that the electron initially is down in a lower state. For example, E initial, it was minus 12 electron volt, and E final, it is minus 7 electron volt, right? So, and the electron will move upward. To move the electron upward, this is upward transition. Upward transition. To move the electron upward, it needs to gain energy. Now you will ask me from where I can gain this energy. Okay, it needs, so here, to move the electron up, to this electron, it jumps upward, have upward transition. To move it up, it needs to gain energy. And this energy should match the difference between these two states, between -7 and -12. So it needs to absorb specific photon. It doesn't absorb any photon, okay? It needs exactly a photon equal to 5 electron volt in order to gain this energy, in order to jump to the higher energy state. So here it absorbs photon, not any photon, 5 electron volt. Only 5 electron volt can move it to this state, to the higher state. So here, to calculate the energy of the absorbed photon, it's equal to the change in energy, which is equal always, the higher energy here is, or the greater energy is final minus E initial. Always I start with the greater value. So -7 minus into -12, so the answer will be +5 electron volt. So to move, to have upward transition from lower state to higher state, it should absorb not any type of photon, specific photon should be absorbed to move here. If I give it 4 electron volt, it doesn't absorb it. 7 electron volt, it doesn't absorb it unless if we have a level matches the difference. Okay? So again, we have two types of transmission, either up or down. In this transmission corresponding to a absorption spectral spectral line. We need to relate what we are explaining here with the emission spectrum and absorption spectral lines we observed before. You understand? Okay. So, as we see, we have upward transition. When an electron absorbs energy, it jumps to higher energy level. If the absorbed energy is exactly equal to the difference in energy of the two levels, as you see here. And downward transition, when an electron jumps from higher to lower energy level, it loses energy as emitted photon. We explained this before. Okay. So, as you see, this is a general formula can be used to calculate the energy of the photon or the change in the energy. You see? So it's we can write it in another form. We can write it as you see, E photon equal. You can write directly E photon, absorbed or emitted. Absorbed or emitted, same idea. Or emitted. It's equal to the change in energy, which is equal to HF, which is equal HC over lambda. Okay. And always, as I told you before, you write the E of the greater or higher minus E smaller to get scalar value. You get the idea? So, E2 means the greater here, the higher energy, the higher energy to get energy photon. This is the lower energy to get E photon positive, to get E photon positive. This is very important. Each transition is represented by an arrow or spectral line. Again, let me imagine here we have many energy levels, and let me draw many transitions. Like this is a transition, this is another transition, this is another transition. You see, this is another transition. All these shown transitions, they are downward transitions. So, okay, and let me show you another type of transition, upward transition. See, this is a transition. These are upward transitions. You see? Sorry. Should be straight. Okay? You understand? So these types, what we call them, downward transitions. And during downward transitions, we have what? Emission of photons. What we have? Emission of photons. You see? Here, during upward transition, we have absorption of photons. What we have? Absorption of photons. Here we have emission of photons. Here we have absorption of photons. For each jump, we have color. We have color. Okay? To understand more what I'm saying here, let me move back a little bit. Let me move back a little bit. Again, remember, we go back to emission transition. Emission spectrum. Here I see in the emission spectrum 1, 2, 3, 4, 5, 6, 7. 7 emission spectral lines means I have 7 jumps. 7 jumps. For each jump, I have a spectral line. You understand? Where down I see 7 black lines means I have 7 upward transitions, mean I have 7 absorption spectral lines. I hope you understand what I'm saying. I need you to relate spectrum with the jumps. Okay. Now the last thing I will explain is the ionization energy. Ionization energy, it is the energy required to completely remove an atom, an electron, sorry, which is in the ground state from the atom. So every time they ask me, for example, imagine here I have atom, and around it you have energy states, right? Till infinity. Till what? E infinity. So imagine you have electron here in the ground state, and you need to remove it completely from the atom. To remove any electron from the atom completely, you need energy. This energy, what we call it? Ionization energy. How to calculate it? It's very easy. It's E infinity minus E1. So every time you need to remove electron completely from the atom, you need to take it to the ionization state. So for hydrogen atom, E infinity is 0 and E1 is minus 13.6 electron volt. If I need to calculate ionization energy for hydrogen atom, simply I write E infinity minus E1, which is 0 minus into minus 13.6 electron volt. So the answer will be positive 13.6 electron volt, which means to remove this electron from hydrogen atom, you need completely from hydrogen atom, you need 13.6 electron volt. Okay. Now we can start solving questions as application on the previous objectives. Starting with question number 1, calculate the wavelength of radiation emitted when the electron in the hydrogen atom makes a transition from the energy level minus 3.4 times 10 to the power minus 18 joule to level at minus 8.5 times 10 to the power minus 18 joule. So we need to calculate. So we start with the idea that energy photon, as usual, E photon, we know E photon equal E. Here, which one is greater, the initial or the final? This one is greater. Minus 3.4 is greater than minus 8.5. So we start with E initial minus E final. You see? We don't need the energy photon. We're looking for the wavelength. So we can replace E photon by HC over lambda. And here, E initial is minus 3.4 times 10 minus 18 minus 8.5 times 10 to the power minus 18 joule. Okay, it's perfect to have the answer in a joule because this side is a joule. So I need to find the wavelength. So I replace these values by lambda to get the final answer. So the final answer will be, after using writing the steps here, so lambda will be equal HC 6.63 times 10 power minus 34 times 3 times 10 to the power 8, which is HC divided by this value. This value, if we subtract them together, we get 5.1 times 10 exponent minus 18. Now, after using calculator, we get the answer will be 3.9 times 10 to the power minus 8, or we can write 39 nanometer. 39 nanometer. Okay, dear students, we continue solving with question number 2. Let me read the question together. The electron in the hydrogen atom drops from the energy level E3 to energy E1. Okay, let me use another color to show the transition. So the electron initially on E3 means here, and it will jump down or make transition down to E1. Right? This is transition. The question asking in part 1, find the energy of the emitted photon. Of course, during this transition, a specific photon will be emitted because the electron is losing energy as forms of photon. Is it clear, or light? So to calculate the energy of the photon emitted, a photon, it's equal to the change in energy, right? Which is E3 minus E1, the greater energy minus the smaller, which will be equal to minus 1.5 electron volt minus into minus 13.6 electron volt. So the answer will be positive 12.1 electron volt. So this is the energy of the photon emitted when the electron jumps or makes transition from E3 to E1. Part number 2. Find the frequency of the emitted photon. For the same photon, I need to calculate frequency. E photon, the same used photon or the emitted photon, it's equal HF. I'm looking for the frequency. So the frequency will be equal, make it subject, E photon divided by Planck's constant. But be careful that this energy must be in joule, not in electron volt. I will show you why. So E photon, how much? 12.1. If we keep electron volt and down you have it joule seconds, the units do not cancel each other. So what I do, I multiply by 1.6 times 10 exponent minus 19. This is what? This is the energy now in a joule, right? And down you have 6.63 times 10 exponent minus 34 joule second. So so the unit of joule here cancel joule, so you get 1 over second, which is hertz. So the final answer will be, the frequency of the photon will be, let me use calculator to get. So the answer will be, after using it, will be 2.92 times 10 to the power 15 hertz, which is 1 over second. The last part, let me read it together. So the first two parts, as you see, they are easy. If the electron moves from E2 to E3, means upward transition. We have upward transition. I will show you this transition using another color. So, okay, sorry. So again, from E2 to E3, which is shorter transition. You see, it's upward and shorter. We said before, if you remember, the size of the arrow represents the energy emitted or energy absorbed. So when the arrow is longer, means greater energy we have. When the arrow is shorter, means less energy we have, less energy photon we have. So to have this transition, the electron must absorb a specific photon. So here, photon, specific photon is absorbed. Okay, for this, okay, for this transition. Okay, now the question is which transition, transition 1 or transition 2, right? Which transition has longer wavelength? The emitted means the first one, or the absorbed means the second one. Okay. Initially, to discuss the wavelength, we need to know that E photon is inversely proportional to the wavelength. To whom? To the wavelength. Means the one with longer wavelength has less energy photon, or shorter transition. Shorter transition. Which is here, which one is shorter, 1 or 2? The one with longer wavelength, again, it has less energy photon. Less energy photon means the shorter arrow, shorter transition. Which one is the shortest transition here? Shorter transition 1 or 2? Of course, it is transition 2, which corresponds to absorption, absorption photon. You see, absorbed photon. So shorter transition, which is the upward transition. Is it clear? Which is the absorbed one. Transition. Okay. Finished from question 2. Okay. Question number 3. We continue the question number 3. Let me read it together. The electron in a hydrogen atom makes a transition from an energy level -3.4, this is E initial, to a level at -1.5 electron volt. So before I start solving these two parts, part 1 and part 2, okay, let me imagine what do I have. I have two energy states. Let me imagine we have two energy states. The initial one, it's -3.4, which is lower. So initially, the electron was down because, you see, -3.4 minus 3.4 electron volt. Then it becomes with more energy, it gains energy, so -1.5 electron volt. -1.5 electron, this is E final. So the movement is from E initial to E final, so it will be look like upward, because it's from lower energy state or energy level to higher energy level. Question number one. What is the type of line spectrum? We know we have two types of line spectrum, either absorption line spectrum or emission line spectrum. So here, to move the electron from lower energy state to higher energy state, this electron needs to absorb specific photon. So absorb specific photon, not any photon, you see, which matches the difference. So here, because it needs to absorb photon, so the type of this spectrum is absorption spectrum. Why? Because the electron is moving from lower to higher energy state. So here, it is absorption line spectrum, because the electron undergoes transition from lower to higher energy level or energy state. Okay. Part number 2. Find the frequency of this transition. So simply here, the frequency, it's inside the E photon, right? Which is equal to the change in energy, which is equal to E final here minus E initial, because E final is the gradient. So instead of E photon, we can write HF, because we're looking for frequency of this photon. It will be equal -1.5 minus into -3.4, so which will be positive 1.9 electron volt. So the frequency we're looking for is equal to 1.9. We need to change it to joule times 1.6 times 10 to the power -19 joule divided by Planck's constant, which is 6.63 times 10 to the power -34 joule second. Joule cancel joule. And the answer will be, after using calculator, so the answer is 4.58 times 10 to the power 14 hertz. Okay.